Welcome back to another session. This time, what we're going to do is focus on numbering systems. And the three we're going to focus on is decimal, binary, and hexadecimal. Okay. Before we go too far, we got to do some definitional work and kind of see why we're even looking at these guys and things of that nature. So numbering systems are important. That's the way we keep track of things in general. And specifically, these numbering systems are very important. Anybody who works with computers, design computers, or has to program it, has to build it, has to maintain it, things like that. So in the numbering systems, we have the decimal, and that basically is saying base 10. What does base 10 means? It means that we have 10 possibilities available to us. As far as the digits, the individual characters representing the number, we have a range of 0 to 9. So if you're base 10, your numbers will go from 0 to 9, one less than 10. Each position will be each number. Let's say if I have a number such as, let's say, 25, base 10, or sometimes we also write it as 25 D. It basically says each digit has value that corresponds to where in the number it appears. So from the right side, we start by saying this is base to the power of 0. This is base to the power of 1, which basically what it's telling us is that I have 2 of 10 and 5 of 1, because 10 to the power of 0 is 1. So that's what base 10 is. Why do we care about that? Well, that's what humans communicate in. And where did it come from? We have 10 fingers. That's simply where it came from. Binary, on the other hand, is a base 2 numbering system. And the reason that is base 2, that's used by computer. And the reason it is because transistors are used as a basis of computers. On and off is the only possible options available to them. So base 2, which means the digits available to us is 0 to 1. And by the way, the digits in the binary system is referred to as bits. Okay, so each digit is called a bit. And one of the things, sometimes you might also hear byte, and byte is really 8 bits are grouped together and called a byte. Byte is kind of important because almost everything in computer is grouped into groups of 8 bits. So when we talk byte, so byte is a very important one. In the past, we used to have nibble, that was 4-bit, but that's gone away. No, that's not an important grouping anymore. Okay, and hexadecimal is more of an interchange. We really don't use it for any specific system. It's just an easy way of taking a large binary number and reducing the number of digits so you can communicate with someone else. And the reason it's useful is because hexadecimal is a base 16, and 16 happened to be the power 2 to the power of 4, which means it's really easy to go from binary to hex and hex to binary. And that's why we use it as an interchange numbering system. Okay, so let's go back up here to a binary. So an example of a binary number would be, let's say, 11001 base 2, or sometimes we write as 11001 binary. But it means the same thing. So that's a number. And as we said before, is that from the right-hand side, the position value of each digit is powers of 2, starting from 2 to the power of 0, moving to 2 to the power of 1, and then 2 to the power of 2, 2 to the power of 3, and finally 2 to the power of 4 here. Okay, so for the decimal, we know that this means 5 with the power of 10 to the power of 0 plus 2 times 10 to the power of 1, and that becomes a 25. Not a very surprising thing. It's a decimal, and 25 is the decimal we get. Okay, now if you have a binary number and you want to convert it to a decimal, you could do more or less the same, except your base is 2. So you have to do a when you go through your process, the powers would be powers of 2. So what you do, you basically take the 1 and multiply it by the power of 0. But whenever it's 0, you don't have to do anything. It's 2 to the power of 1, 2 to the power of 2. And then you got to take this one and multiply it by 2 to the power of 3. And this one multiplied by 2 to the power of 4. So if you want to make its decimal, all you do, you take those digits, 1 times 2 to the power of 0, plus 1 times 2 to the power of 3, plus 1 times 2 to the power of 4. This is a 16, this is an 8, and this is a 1. So you got a decimal value 25 base 10 if you sum them up. Oh, so this number 11001 binary is 25. Great. And then the decimal, the hexadecimal values, we could do a similar thing. So let's say somebody gives us a number which is 19 hex, and say, okay, you can either write it this way or they can write it this way. Both of those are, but the same as before. The place value starts from right, base to the power of 0, base to the power of 1. And if you have more digits, it would be 2, 3, 4, 5, and move on. So to find out what the decimal value is, just take the number, multiply by its place value, take the next number, multiply it by its place value. And there you have it. 9 plus 16 is 25. Oh, okay, so that's the same number as well. So that was pretty easy. So we can basically take any base and convert it to decimal using the same technique. We only showed it for binary and that's hex, but you can do it for any place value you want to, of any base you want to. So the next thing is, let's say, okay, now what if somebody gives me a decimal value? Somebody gives me a decimal value and says, okay, convert it to a binary value. Okay. There are 2 options available. They're equally good. It's up to you. One is it doesn't use division, so it's a little faster for computers because it uses subtract and subtract to do it. Another method uses division. So let's use the subtract method, which is the one given in the textbook, and then we'll go and look at the one with division. So let's say method 1. We'll call this one method 1 subtraction. Okay. So what we're going to do in order to do this one, let's pick a number. Let's pick a number. Let's say the decimal number is 50. The decimal number given is 53, and they're asking us what is the binary equivalent of that. So the method works like this. You find the largest power of 2 that's less than 53. And if you go through powers of 2, you'll find out you got 2 to the power of 1, which is 2 to the power of 2, which is 4. And you finally get to a place where you say, if I look at 2 to the power of 5, that's the largest power of 5 that's less than 53, because 2 to the power of 6 would be 64, and it would be over 53, so you can't use it. So it's 32, and all you do is subtract it. And if you can subtract it, if 32 is smaller than 53, you do the subtraction and you say the bit corresponding to that is equal to 1, because you could subtract. Then you take this up here and go 21 minus 2 to the power of 4, which is a 16, and that will be a 5. Yes, I could subtract this, so this would be a 1. Okay, and then I'll take that up here and do the same to 2 to the power of 3 is equal to 8. Can I subtract? No, you cannot subtract, so you get a 0. And then 5 moves over. 2 to the power of 2 is 4. Can I subtract? Yes, you can subtract, so you get a 1. Remainder is a 1, so I take the 1. Can I subtract to the 2 to the power of 1? No, I cannot do that, so I get a 0 here. And then what is next? The next is the one moves over here and say, can I subtract it from to the power of 0? Yes, you can. Remainder is 0. Since you could subtract, it's 1. So your binary number from this scheme was 110101. So if you want to test it to see if it's indeed the right one, all you have to do is take the place values. This is 2 to the power of 0. This is 2 to the power of 2. This is 2 to the power of 4. This is 2 to the power of 5. So 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 2 plus 2 to the power of 0. If you do that, that's 32 plus 16 plus 4 plus 1 gives you 53. And you're good to go. Okay? So indeed was correct. That's one method. So the other method, if you're doing it as a human, then you don't care about computation speed and hardness of doing division, then you can come over here, and instead of doing it this way, you can use method 2 division. Instead of starting from the left, you're starting from the most significant bit, working yourself to the most right least significant bit. You can do it, you have to do it the other way around. So we give ourselves a little bit of room. So you come here, you put the 53 in here, you divide the 53 by 2, and you write the quotient, but it's a result of a divider, and you're the remainder. Okay. If I do the division, I get 26 is the quotient and a remainder of 1, and that becomes my least significant bit digit. And I'll take the 26 up here and divide it by 2 again, and this time I get a 13 with a quotient of 0, so that's my next digit. Then I take the 13 up here, divided by 2, and I get a 6 for the quotient, 1 for the remainder. And then I take the 6 up here, divided by 2, and I get a 3 with the remainder of 0. Then I take this 3 up here, divided by 2. I get a quotient of 1, remainder of 1, and the 1 comes up here, divided by 2, quotient of 0, which means I'm done, and a bit of 1. So 1, 1, 0, 1, 0, 1, base 2. And if we go back and look at what we had got before, is the same number. It's just two techniques to do the same thing. As far as difficulty, they're just about the same for humans, but for computers, for large numbers, that might be a little faster than the other one, just because it's not a division. Although we can that's good enough for now. Okay, so that's pretty much it. Now the next question that pops up is, okay, so what is the deal with hex? Why do we care about hex? We know how humans work. We know how computers work. We know how to go between binary to decimal. We know how to go from decimal to binary. Why do we even need hex? The reason we like hex is because hex is very quick and it's easy for the number of digits are a lot less, so it's easier to communicate it with other folks. So let's do one. Okay. The beauty comes from the fact that 16 is power of 4, 2 to the power of 4, which who cares? What does that mean? That means when I take a number, let me just take a number, 1, 1, 0, 1, 0, 0, I'm just making this up. Okay. So let's say this is a binary number, and they want you to go to hex. All you have to do is you have to group of 4 from the right-hand side. You start from this direction, and you group things together. So this is, oops, doesn't like me doing that. Okay, there's something here. All right, there's 4 here, there's 4 here, and there's 4 here. Okay, now that's fine. I'll do this, and then I'll come. So this was if there was not 4 digits, you add 0 to the left to get 4. Okay, if there is not, then don't worry about it. So what we'll do here is this is going to be a 5, this is going to be a 2, and this is going to be a D, right? And that's your hex value. Okay. Let me do one more example. This time I'm going to have a number that is not multiple of 4, just to make sure everybody's okay with that. So let's say the number given is 1001, 1001. I'm going to make it something different. Let's say this is the number given to me, and say, okay, find the hexadecimal value for this. So I'm basically doing the same thing. I'm going to group these two groups of 4. And this one is only 2. So what I do, I add what they call a trailing 0. They don't change the number, they just fill it in. So basically, this is going to be a 4, this is going to be a 7, and this is going to be a 2. So that's going to be my hexadecimal number. To go the opposite direction, you do the same thing. You take the 4 and write it in 4 binary bits. Take the 7, write it in 4 binary, and 2. So it's just really easy. So when I have, let's say your computers, most of your computers are 64 bits. So if you just want to communicate one statement from your computer to somebody else, you got to write 64 ones and zeros. What are the chances of an error doesn't creep in there? Chances are pretty high you're going to have an error when you communicate it. So doing it in hexadecimal is a lot easier. It's a lot easier to say 274 hex than do this. That's the only reason we have hex. So that brings us to the end of conversion and numbers and the bases. Oh, another name for base. I just want to make sure this is kind of general information. Some people refer to that as radix. Okay, so it's nothing different. Radix is another name for base. So radix 2. Radix 10, base 2, base 10, same stuff. Okay. Now, in your text, you are introduced to Ascii, which is American Standard of Coding. It's pretty much used, commonly used coding for that. For let's say when you get a character on your screen, let me actually put this in someplace where I can write on it. So this is an Ascii. This is referred to as the Ascii. Is a coding table. So when you're on the computer and computer types Google, okay, what it's really doing in the memory of the computer, there are bytes, there are 8-bit segments, one corresponding to G, one corresponding to this. What is displayed on the screen is just an image, it's just a picture. G is just a picture that putting on the screen for your satisfaction. In the memory, the way the computer knows what a G is basically going to go to this table and it's going to look at G. Here is G. So it's going to be hex 47. So G is a 47, which means in the memory, it's storing 0, 0, 1, 0, 0 for the 4 and 0, 1, 1, 1 for the 7. Little o is right here. Is 6F. So in the memory, what is got stored is basically 0, 1, 1, 0 for the 6 and 1, 1, 1, 1 for the F, and so on and so forth for the second F, and then on and on. So if you look at the memory for the bytes, that's what you see. So Ascii's existence still being used very commonly. But most computers nowadays are using something called extension of, it's literally an extension of Ascii called Unicode. Why is that? Well, Ascii only have room for 8-bit. Each one of these characters are 8-bit, which means the maximum number you can represent, minimum number is 0. The maximum number is 255. So you can only have 256 unique numbers that you can represent. For English, that was perfectly fine because we've got 26 capital letter, 26 small letters, 10 numbers and a bunch of different characters, and we were good to go. 256, but we didn't have extra. We only used 128 of them. We used half of it. Half of it wasn't even used. So what happened is that they came up with this concept of Unicode. This time the Unicode has 2 bytes in it, which means I can have bits from 0 to 15. So I can have 16 bits. So I can have 2 to the power of 16 possibilities. That's all the 32,000 or more possibilities. So I can represent a lot more characters than I could represent with an ASCII. And why is that important? That wasn't important until internationalization. Well, I'm sorry. You can represent 60. I think I said 35,000. You can represent 65,536 possibilities. So this became important when we started translating or having things in Japanese or Chinese or other languages that have 2,000, 3,000 or more characters that have to be uniquely used to represent things. And as such, they would have just fit in an ASCII for that. So then we start working on Unicode. And pretty much most things are in Unicode. Unicode is extension of it. Extension of ASCII, and we can talk about how. So they're interoperable with each other. So you can literally look up any language, any known human language, and most likely there is a Unicode equivalent, a Unicode character set for it. That's not true of ASCII. ASCII is predominantly a Romance language, English, French, German type of a system. Okay, that brings us to the end of this section of numbering and coding and for characters and things of that nature. Thanks for listening.